maybe there are principles, very economical, very powerful principles, which we haven't yet figured out, which will resolve the paradoxes we have, such as the dark matter, the dark energy, the Big Bang itself, what goes on in black holes. They're very, very basic paradoxes. Mm-hmm. And maybe we just need to think a little harder. So after I've started following this line of research about 5 years ago, it's very difficult because you've essentially tied your hands together. I'm not allowed to introduce a new particle, okay? But we've made amazing progress. At least I find it amazing. We've realized what the dark matter is. It's probably a right-handed neutrino, which is already there in the standard model. It's extremely economical explanation. We've found, this is something I'm most excited about recently, a new explanation for why the universe is so simple on large scales. The geometry of the universe. What is the universe like on large scale? Well, in first approximation, it's flat space. It's the thing you learn about in geometry in primary school. There's X, Y, and Z. There's no curvature at all. Why is it the simplest possible geometry? It's a huge puzzle, which motivated the theory of inflation. So now we have a new explanation. And the explanation is extremely economical. It doesn't make it easy to understand, but it basically developed Stephen Hawking's ideas about black holes. And we literally do a calculation of the thermodynamics of the universe, which I'll say very briefly, shows that, just like the gas in a room will distribute itself evenly in space, because that is the most probable configuration of the atoms. If you chuck them in with some energy, allow them to randomize, they will spread themselves out uniformly in a smooth distribution. You don't have to introduce somebody to smooth that or do something active, another field or particle. It just does it itself. That's thermodynamics. Mm-hmm. And so we figured out the thermodynamics of the cosmos using Hawking's insights, and with no finagling with new particles or whatever, with some very simple mathematical assumptions, we find the most probable universe is flat. Exactly the geometry we see, and it's the simplest geometry. And so that's an entirely new explanation. It doesn't require any new ingredients. It will take people a long time to accept this. Well aware of that, because people have built their careers for 40 years on different assumptions. But I'm personally very excited about it. I think what we're seeing is a way through to explain all the puzzles, all the major puzzles in theoretical physics, with absolutely minimal additions to what we already know.
Well, there was a man who was an alumnus of your fine university, who had a bit of experience with simplification, with unification, and with really constructing a strict mathematical model of the universe. And it worked pretty well, except for the fact that it was also based on very simple principles involving gears and vortices and whirlpools. And of course, we're speaking about the late, great James Clerk Maxwell, who's a towering figure in all of science. And maybe, in the spirit of a Higgs or a Yang-Mills, or in the same way. What do you make of his ultimate, what he did, Neil, is so interesting, because he was absolutely correct for all the wrong reasons. And we see that again and again in science. We see that with Galileo. He was right about universal gravitation, or Newton was right about universal gravitation, completely wrong about how it propagated. Galileo was completely right about the orbit of the Earth around the sun, thought it was responsible for the tides. That proved it had nothing to do with the tides. But tell me, Neil, is it possible sometimes that brilliant theorists can have the right idea for the wrong reason, and in that way, give us a glimpse of truth. And maybe could that be happening with inflation in the multiverse? Just to be a little bit of a steel man in
Yes.
yeah.
Yes. No, it's a good question. And it's a big puzzle why inflation and the multiverse have become so popular. Because objectively, this is a theory with an infinite variety of models, of lots of parameters, lots of freedom, extremely hard to prove wrong. So on the face of it, it's a theory which isn't particularly scientific. Traditionally, it would be regarded as unfalsifiable and therefore not part of science. But what's happened is the field of theoretical physics has kind of been pushed into a corner where many of the luminaries, I mean, very great theorists like Steven Weinberg, who was more or less a founder of our modern picture of physics and the Standard Model, came around to this point of view of the multiverse and inflation. And I always found it sort of surprising that they did, but they did for what you could say were good reasons. I mean, there's a certain logic behind the steps people followed, but it's just a case of when you make one false turn, and there's no kind of experimental check or insufficient experimental checks, you can very easily go wrong. And so I think that's what's happened. I think, in fact, around the time I entered theoretical physics, in the 1980s, that's when the field went wrong. Okay, I'm not saying it was my fault.
Stephen had something to do with it. I think Stephen Hawking had a little bit to do with it. He actually in A Brief History of Time, which I went back and read shortly after his death. He makes a big deal about not only is there no boundary, is there no beginning, but that the CMB basically proves that there is inflation, there is a multiverse, and he really went quite and he's so influential. Although my first ever guest on the podcast was Freeman Dyson, who I loved and was incredibly influential. I'm sure you knew him when you were a professor at Princeton as well. And many interactions with. He said the safest thing in life to do, Neil, is to make a bet with Stephen Hawking, because either he was wrong ab initio, or he would eventually switch positions, so you would win no matter what.